Hello, good people. This is section 3.5 of James Stewart's Calculus Early Transcendentals book, and we are on the topic of derivatives. And today we're going to go over implicit differentiation and what its process is. So up until this time, we have been going over the rules for derivatives with explicit functions. In other words, we've got a function y that is explicitly written in terms of x, y is solved for. But we've got graphs of relations and other equations that could be solved for y explicitly, but they need to be defined piecewise, such as circles and ellipses and things that we might still want to be able to find slopes of tangent lines and their rates of change on. So what is an implicit function? Well, it's exactly that. It's an equation in two variables where the dependent variable has not been explicitly solved for. The y equal to f of x, x is the independent variable, and the value of y depends on the value of x for its output. So here we're going to still work with a function that is just an equation in x and y, and neither one is explicitly solved for, but we can still find what the derivative is. But we do want to implicitly or imply that behind the scenes y is still a function of x, so that if I were to take a derivative of my implicit or go on my way to find dy dx, if I had y to the n, I would want to use the chain rule here, and if I take the derivative of y to the n, it would be y to a number, and I'd be saying that that's n times y to the n minus 1, but since behind the scenes y is a function of x, then I still want to multiply by the derivative of the inside. So in other words, employ the chain rule. Since we will have variable x in there, some of the basic ideas around taking implicit differentiation is step 1, take the derivative of both sides of the equation. And keep in mind that terms that can't contain just x take the derivative normally. So terms only in x get regular differentiation. Did I write that wrong? And terms that contain y and only y get the chain rule. So don't forget to multiply by dy dx, and assume that behind the scenes y is a function of x, and terms, or that products of x and y get the product rule and the chain rule, and you'll see that, and quotients of x and y get the quotient rule, and compositions of functions definitely get the chain rule. And so once we have differentiated both sides and we actually do have dy dx among some of the terms, we actually end up having an equation that is linear in dy dx. So the following step after that first differentiation of every term on both sides of the equation, we just want to isolate the dy dx terms on one side and the terms that do not contain dy dx on the other side, factor out the dy dx, and then divide by the coefficient. So you're actually just solving for dy dx. Now you're going to end up with an equation for dy dx, or solution for dy dx, that has both x and y in it. And that's okay, because we have our original function, or our original relation, that is the relationship between x and y. So we can still find slopes of tangent lines. It's just that instead of only requiring the value of x from our original function or relation, we'll also need y as well, just to find that. So let's actually do some examples here so that you get the idea of how to find the derivative dy dx. And after doing that, we'll move forward and say, well, how can we find the second derivative so we can find concavity, or the acceleration? All right, so I wanted to move forward and do this one here, just since we did not do this in class. So here, consider the equation of the tilted ellipse. All right, so this is not a function, but it is a relation. But now, you know, we could, if we could solve for y, we'd probably have to solve for it and have it be a piecewise defined function so that we would have the whole graph. But here we can keep it in its implicit form, and you can tell that this is just a relationship between x and y, and those values that make the statement true form the tilted ellipse in the plane. So here it says, find the equation of the tangent line to the curve at the point. So my first step is that I'm going to take the derivative of both sides, term by term. X terms have standard differentiation, y terms have the chain rule, and products of x and y here are going to get the product rule. So here we go in my first step, and I'm going to take the derivative of x squared, which is just 2x, plus xy, that's the product rule. So the derivative of x is 1 times the second, plus the first, x, and then times the derivative of the second, and the derivative of y is 1 times dy dx. So I just say it's dy dx. And then the derivative of y squared is going to be 2y times dy dx. The derivative of 1 is 0, and the derivative of 0 is 0. So now I have an equation in dy dx, and I'm going to solve for dy dx. So my next step is solve for dy dx. And that means isolate and divide by the coefficient. Okay, so I'm going to keep the dy dx terms on the left-hand side, and I'm going to move the other terms that do not contain that on the right-hand side. So I have x dy dx plus 2y times dy dx equal to, and I have minus y minus 2x. I'm now going to factor out the dy dx. And then I'm going to divide by the coefficient. So here's my dy dx, and that's going to be minus y minus 2x over x plus 2y. So that's my derivative equation or solution. And notice that it is in terms of x and y, but I can still find the slope of the tangent line. I'm just going to need both the values of x and y. And we have the value of x and y here, and I'm going to, for foreshadowing, that's going to be our x1, y1. And so for our slope at 1, 0, we're going to be evaluating the derivative at xy equal to 1, 0. And that's just going to give us minus 0 minus 2 times 1 over 1 plus 2 times 0. And that's going to give me minus 2 over 1, which is just minus 2. So that is my slope, m. Okay, and then we know in finding the equation of our tangent line, we use our point slope form. So that's going to be y minus y1 equal to m times x minus x1, and I'm just going to plug in my values and solve for y. And what are my values? I have my y1 is 0, my slope is minus 2, and my x value is 1. And when I clear my parentheses and solve for y, I end up with minus 2x plus 2. And that is the equation of my tangent line at that point, 1, 0. And I can kind of tell, because here's my point, right? And if this is 1, then 2 is going to be kind of up here. And if I go down 2, 1, 2, and over 1, I get to my point, and I can, if I connect the dots, I can see that that makes sense, right? And that's my tangent line. Okay. Now it is possible, if you've got an equation that you can easily solve for y, you can go back and solve for y and then just take the derivative explicitly, and you would have a dy dx that is exclusively in x, and that's fine, but it's just taking the extra step of solving the equation for y. But this is an example of it'd be difficult to solve for y, and so why would you do it? All right, so let's do some other examples, and I have a couple down here. And let's do this again. So let's find dy dx. And here we go. So again, step 1, take the derivative of all sides, or all terms, and we have the derivative of 2x squared is 4x plus x times y. That requires the product rule together with the chain rule for y. Y always gets the chain rule. So the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second, and the derivative of y is 1 times dy dx. And then we have minus y squared, so that's going to be minus 2y dy dx, and then I'm going to end up with the derivative of 2 is 0. My next step, solve for dy dx. So in solving for dy dx, I'm going to keep the x dy dx on the left-hand side. I'm going to keep the minus 2y dy dx, and I'm going to move the other terms on the other side. So I end up with minus y minus 4x. I'm going to isolate the dy dx by factoring it out. And then I'm going to divide by the coefficient. And so I get minus y 4x over x minus 2y. And this one seems to be very similar to what we just did. So let's do one more. And that is my derivative. This one. I see e to the x over y equal to x minus y, and we want to find dy dx. Okay, so in my first step in differentiating both sides, I do see e to the x, so I need to use the chain rule, but then I also need to take the, in using the chain rule, we have e to the x evaluated at the inside, but then times the derivative of the inside. And whenever I see a quotient of x and y, I need to use the quotient rule, but also every time I take the derivative of y, I need to use that chain rule every time. So here, in multiplying by the derivative of the inside for our chain rule, our quotient rule is the derivative of the top times the bottom minus the top times the derivative of the bottom, and the derivative of the bottom is 1 times dy dx, all over the bottom squared. And that is the derivative of e to the x over y implicitly. And then equal to the derivative of x is 1, and the derivative of y is 1 times dy dx, which is just dy dx. Now I want to solve for dy dx, right? That's our next step. And the first thing that I'm going to do is I'm going to multiply on both sides by y squared. So I'm going to have e to the x over y times y minus x times dy dx. And that's going to give me y squared times 1 minus dy dx. Now I want to clear my parentheses and isolate dy dx. So I'm just going to clear my parentheses on the left-hand side, and I'm going to get y times e to the x over y minus x e to the x over y dy dx. And I'm going to distribute my y squared, and I'm going to get y squared minus y squared dy dx. I'm now going to isolate my dy dx on one side. So I'm going to add y squared dy dx to both sides, and then I'm going to also subtract y e to the x over y from both sides. So I'm going to add y squared dy dx to both sides. And then I'm also going to subtract minus y x over y. And I'm going to do that here. Good, so that on this side it goes away, and on this side it goes away, and I end up with y squared dy dx minus x e to the x over y dy dx. And this is going to equal y squared minus y e to the x over y. I'm now going to factor out my dy dx. And then I finally divide by my coefficient. So in dividing by my coefficient, I end up with dy dx is equal to y squared minus y e to the x over y over y squared minus x e to the x over y. And there's no way to simplify that, and that is the formula or expression for dy dx. And we're going to learn to be happy with little complicated scenarios. Okay, so how would we find the second derivative? Okay, so obviously we're going to first find dy dx, and then when we take the second, it's going to be in terms of x and y, just like what we have up here. And so if we were to take the second derivative, it would still be an implicit expression. And so every time you see a y term, you use the chain rule. Every time you see an x term, you take derivatives normally. And anytime you see a product or a quotient, you've got to take of x and y, you need the product rule or the quotient rule. And again, with compositions as well. So it's usually best described using an example. And so here I'm going to find the second derivative. So first off, let's find the first derivative. And we do it implicitly. And so we're going to say this is 3x squared minus 3y squared times dy dx. And the derivative of 7 is 0. Next, I'm going to solve for dy dx, and I end up with minus 3y squared dy dx is going to equal negative 3x squared. I'm going to divide both sides by 3y squared or minus 3y squared. And I get minus 3x squared divided by minus 3y squared, and that's going to give me x squared over y squared. So that is my dy dx. So if I have dy dx equal to x squared over y squared, this is still implicit, okay? So when I take y double prime, that's going to be the derivative with respect to x of dy dx, and that's going to be the derivative with respect to x of x squared over y squared. And again, we have the quotient rule. So the quotient rule tells us the derivative of the top, this is, and finding the derivative there. The derivative of the top is 2x times the bottom minus the top times the derivative of the bottom, and the derivative of the bottom is 2y times dy dx, all over the bottom squared. So that's going to be over y to the fourth. Now, this is an expression for the second derivative, but we actually want a formula that only contains x and y. We don't want one that contains dy dx. So what do we do with the dy dx? We go back to our expression for dy dx and we substitute that value in. So this is going to equal 2x y squared minus, and I'll clean things up just a little bit, 2x squared y times, and I want to plug in my x squared over y squared. Good? All over y to the fourth. And now I want to clean things up because I've got a complex fraction now, and since we don't like fractions to begin with, we want to get rid of that fraction. So I can, a little bit, clean things up here by canceling my y with my y squared to give me y, but I still have that denominator y. And normally, in that case, I'm going to multiply on the top and bottom by the lowest common denominator, and the lowest common denominator here is going to be y over y. Oh, what happened there? Sorry about that. I clicked on something and it went over. So y divided by y. And now I'm going to distribute. So I'm going to distribute here and there. Good, so I end up with 2x y squared times y is 2xy cubed, and then minus, and then this y cancels with this y, and so I just end up with, and then x squared times x squared is x to the fourth, right? Over, right, y to the fifth. That's just multiplying my two terms. So this is my y double prime. Hopefully that was clear, and I will